So today, at first, I would like to discuss, how to develop a complicated code. I will take one quiz question as an example, the quiz 2-4. And after that, we enter chapter 3. So chapter 3 deals with the random variables. Maybe I think that most of you have taken basic statistics course, so you know that what is random variable, but we learn how to deal with random variables in our language. So several functions. We have like the statistical concepts such as PDF or CDF or random numbers or density functions, and what functions are used in R to deal with it. And chapter 3 also includes some simulation component. So it's natural that if we deal with random numbers, that we can do some simulation based on it. So that is the chapter 3. And at least I would like to finish the first maybe 21 slides in chapter 3. Okay, so at first, so I will share the screen to explain one of the quiz questions. I think that I got the most inquiries on this question. And yeah, chapter 2, quiz 2-4, maybe it's a little too small. Yeah, so this is the question. So by using a while loop, find the smallest natural number n such that summation of j is equal to 1 to n log of j is larger than 100, where log means natural logarithm. So this is a kind of complicated question. Once we need the for loop, while loop, or something, that it's complicated. And for this kind of question, just to start, simple one first. Then later that we just make more abstract code. So that is my recommendation. And if you see solutions of any quiz question, that you only see the final answer. But to get the final answer, you need steps to get it. So just I would like to demonstrate how to make code. Okay, so at first, interpret this equation. So this is the the first step to solve the question. So summation of j is equal to 1 to n log of j. So that is like the log of 1 plus log of 2 plus log of 3, right? And actually, this is 1.79, so it's not larger than 100. But if you add this more and more, then it gets larger and larger. So, and at least if the number inside is larger than e to 2.718, then this summation becomes at least 1 larger. So at some point, probably before 100, this summation becomes larger than 100. That is the we can see. So we want to get if this is larger than 100. So basically, we judge this kind of condition by increasing number of terms. So that is what we want to do. So there are several ways to do this, but for example, you can simplify this code of log of 1 to the summation of log of 1 to 4 as, okay, so at first, the log of 1 to 4 can be obtained by this. So this is at least simpler than this. Right? And if we want to take summation, then summation of log of 1 plus 4. So we can write in this way. And you can see if this is larger than 100. And basically, we want to do this for, but replacing this, second number by, any other, increasing sequence of integers. So the 4 is not large enough, but we want to plug in 5, 6, 7, and so on. So we want to get this as 5 or maybe 6, 7, and until it becomes true. Right? And yeah, actually we can do manually, but probably we want to use while loop. And basically we have to change this number. Right, so we make it this number larger. So basically, we want to get this for increasing sequence. So maybe we get the n is equal to, okay, so 8, then we want to write the log of 1 to n is larger than 100. So, and we want to change this n from maybe 1 to 2, 3, 4, 5 until this condition is satisfied. Right. So in this way, at least, okay, so this statement can be used as a condition for a loop. So yeah, so you can use the while loop or repeat loop, and within this condition, at least one way to do is this. Then if the n is not large enough, then we increase n by 1. Right. So in that way, we can solve this question. Okay, so this is almost answers question. And probably this is not most efficient code, because every time we create a new sequence of 1 to n. Right. So if you know this one, just we have to add the log of 5. So maybe you can modify this code for more complex, more efficient code. But this is basically, what we should do when we do coding. So just check step by step. At first, see if this works good or not. And maybe even I type log of 2 first and a log of 3 first to see this is natural logarithm. Yeah. So if log of 3 is less than 1, then probably that logarithm is log with base 10, right? But here, log of 3, 1.09. So at least we see that the base of this logarithm is probably e. So just the step by step. So if you see the solutions of any questions, you can immediately see while of this, the condition or something, but you don't have to come up with it in one step. You can do this one and this one and so on. And at some point, you want to make a code with loop or something to automate some procedures. Yeah. And also, if you get some error, I recommend you to do just one by one. For example, for I is equal to the 1 to 100, maybe. Okay, so suppose that the x is numeric vector of 50 observations, and maybe 10 observations. Okay, x is this. Oh, sorry, numeric this, and okay, x is this. And suppose the for loop I is equal to 1 to 12, and the ith observation of x is the I square or something like that. Okay, sorry. This does not really work. It actually works. Okay, so this is a little strange. Just I want to make a code which does not run. For example, actually it worked. Yeah. So for example, x is 0 and maybe y is a vector of -1 and 1, maybe. And for I is equal to I to 10. Maybe that z I is equal to xi is larger than y or something. Then it becomes error. Actually, the object z does not exist, so that this exactly see the problem, and the z does not exist. But also, even we modify something, so even if we have the object z, probably this code makes some error. And okay, so many warning messages, so we are not sure what's happening. But if you run code, just once, the step by step, we can see why this kind of warning message appears. So okay, so if we have for loop, I is equal to 1 to 10. This is a kind of abstract code because we are using for loop. Okay, so the more concrete example is, okay, I is equal to 1. Okay, I is equal to 1. Then what happens when, we try to define that z of 1 is equal to this one? Or still we have warning message. Okay, so this is a kind of complicated code because we define z based on condition of x and y. So probably we should try this one first. Then, okay, so the problem we can see is here is that if we put this condition, actually we have two outputs, right? So z of 1 is just one element, but we have two outputs. So that's why we got warning message we can see. And why we have two outputs? Then further, we can just type x of 1. So okay, so this is one number, but the y has two numbers. So we are comparing one number to two numbers. So that is strange. So that is basically the source of these warning messages. So if you type this one and you immediately see these 10, the warning messages, then you cannot really see what's wrong with it. But if you decompose this into simpler pieces, then you can see what's your problem. And so this kind of thing does not appear in the solution. Solution is a perfect, the code, and it, skips all, intermediate steps. But when you code it, then basically you have to start from simpler code. And also, if you encounter any errors, then you decompose this. If you have for loop, you plug in some concrete number, I is equal to 1 or 10 or something, 5, then you see that what happens with this code. And even if this is complicated, just you can go step by step. What is z of I? What is x of I? What is y? And also sometimes the code stops in the middle. Maybe I is equal to 1 to 5 is fine, but the 6th observation, we have some error. For example, x doesn't have 6 observations or something like that. So in such a case, after doing for loop, you can check when the code stopped. So maybe it stopped when I is equal to 1, or it stopped when I is equal to 5. That is different situation. If it stops when I is equal to 1, probably this code has fundamental problem. But if it stops at I is equal to 6, probably this code may be fine for some cases, but we have some minor errors. So in that way, that we can code, we can debug the code. Yeah. Do you have any questions for R coding or other quizzes? Okay, so just I want to explain some know-hows to code, because the solutions doesn't show this kind of explanation. Oh, sorry. Yeah. Yeah, so now that we go to chapter 3. Chapter 3, I think that I have to use both slides and our sessions to explain. Okay, so chapter 3, the probability and the distributions. Actually, the first part is the random sampling. So this is a kind of simulation method. So to randomly select numbers from a finite set, maybe set of 5 observations, use a sample function, the SAMPLE function. So this function is used for resampling methods. Resampling means that we sample from the sample. So suppose we have 10 observations that we want to see the average weight of Wayne State University male students, then we have sample of 10 male students. Okay. Then 10 observation, 10 students is a sample, but we further sample out of those 10 observations, right? So we have 10 students, but we take 5 of those, or we take 3 of those, or something like that. So that is the so-called resampling. And resampling is sometimes useful to evaluate the variability in observations. For example, if we have 10 male students, and we know those average, the heights of those 10 students, and we can calculate the mean heights, right? So if you calculate mean heights, okay, so that is 175 centimeter. But we don't know how reliable those 175 observations, right? Because we only have one sample. If we have maybe another sample of 10 students, then average is 173 centimeter. Okay, so first one is 175. Second one is 173. So we have some variability we can see. But usually, we only have one sample. And also if you have 20 observations, probably you want to take average of all 20 observations. So then how to evaluate how reliable that average is? Then the one way is resampling. So out of, for example, the 20 observations, we sample just the 10 observations several times, then see some variability. Then we can see some variability in data. So that is the idea of resampling. Yeah, so resampling methods evaluate the variability of statistics such as mean and standard deviation by simulation. Yeah, so I had an example of the sample mean, but for other statistics also we can calculate it. For example, if we have 10, the heights of WSU male students, then we can calculate standard deviation of it. But how reliable that standard deviation is, we cannot really see. But if you use resampling methods, we can evaluate the variability, or maybe median or maximum or minimum or something like that. Yeah. Yeah, so that's the case. For example, think about the tallest student at Wayne State University. Suppose we take the 10 Wayne State University male students, and the tallest person is 210 centimeter. Okay. Okay. So Wayne State University, maybe typically the 10 students include a student whose height is more than 210 centimeter, but that is probably not likely. Just one student is very high, just by chance. But if we have 10 students and the resample 5 students out of 10, then those 5 students may have highest height of maybe 185 centimeter or 179 centimeter. Then you can see maybe 210 centimeter is kind of an outlier. And within 10 students, we have one student who is very high, but typically not that high. So we can see that kind of information. So that is the idea of resampling. Okay, so how to sample observations? So we can use this code. Sample 1 to 10. This is a sequence of 1 to 10 and 5. Then we take 5 observations out of 1 to 10. So one example is 6, 5, 9, 2, 8. If you run this code again, we get different numbers. Okay, so you can see. So this 2, 8, 3, 9, 6, 7, 6, 1, 3, 2, 1, 2, 4, 7, 10, and 7, 10, 9, 1, 6. So every time, maybe different sequence. And actually, the no duplications are allowed. So all 5 observations are, always 5 observations are different. So this is the sample function. So if you take out the 10 observations, then this is a kind of the randomized the order of these 10 observations. And actually, if you omit this, actually the default value of the number of observations to be taken is 10. If you type 11, it returns an error because it's impossible to select 11 out of 10 without replacement. So this is sample 1 to 10. And if you type replace is equal to true, then we get possibly the same observation twice, 10 and 10 here, and 4 and 4 here, and 2 and 2 here. But 1 or 5 or 9 do not appear in this case. So yeah, so this is this looks a little strange idea, but this is a kind of reasonable because if we have 10 observations from 1 to 10, we can interpret it as 10% of observations are 1, and the 20%, 10% observation, another 10% of observations are 2, and so on. And each time we pick up the number out of that distribution. Okay, so 10% 1, 10% 2, 10% 3, and so on. suppose that that we have a larger set, but the 10% of observations are 1, another 10% is 2, and so on. Then this is a kind of
I have a question.
simulated. Yeah, sure.
Is it from a normal distribution that you're getting the value from?
No, this is from just the sequence of 1 to 10. So in statistical sense, uniform distribution on these 10 observations, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Random numbers that we will discuss it later in this chapter. Yeah, good question. Okay, so sorry. The sample 1 to 10, 11, that makes an error. But the sample 1 to 10, 11 with replacement option is equal to true. So this returns some sequence because we can take the same observation multiple times. So we can make the sequence of any length. So here length 11 and 12 and so on. Of course, in some cases, they're just by chance, there are no duplications. For example, sample 1 to 10, 5, replace true, then, okay, so this one doesn't have any duplication, but this is just by chance. If you try several times, sometimes we have replacements. Any questions on sample function? Yeah, again, so this is just basically random numbers out of this specific number of observations. So basically the uniform random variable in some sense. And of course, we can take the observations out of different vector. So in the previous slide, just 1 to 10. But we can take sample out of these 4 numbers. That's also possible, 1, 2, 4, 8. And we take 3 observations out of this. Then 2, 1, 4, or maybe 8, 2, 1, or 4, 8, 1, or something like that. And we can do this for character vector ABC. In such a case, we are thinking about basically the set of these 3 observations ABC. So if you do sample from this for 5 observations with replacement, then we can get the BCCCA. And also, we can specify the probability for those observations. Suppose that we only have 2 elements A and B, but the A happens only with 20% probability, and the B happens with 80% probability, then we can do in this way. So sample CAB 10, replacement true, probability 0.2, 0.8. You can see this is a vector of 0.2 and 0.8. Then answer can be this. So B appears with 80% probability each time. So actually, in this case, 9 Bs and 1 A. But that is natural. If B happens with 80% probability, maybe we have 7 Bs or 8 Bs or 9 Bs. Maybe a rare case is we only have 5 Bs or we have 10 Bs. Yeah, but that can be done with this. So obviously this is useful. For example, blood type, the distribution is not uniform. Any questions? Yep. Okay, the next one, suppose that we have 5 observations, maybe the weight of newborn babies, 5 observations, and we can calculate the mean and the standard deviation of the data. And yeah, so, okay, so then we can also estimate the standard error of the sample mean. Okay, so basically, when we have 5 observations, we have sample mean, but we have, the reliability of that sample mean. If we have another 5 observations from the same population, how reliable it is, we can make that. So we can calculate the standard error of the sample mean, and also we can estimate the standard error by resampling method. Okay, so at first, if we have these 5 observations, okay, we define this as maybe lowercase x. the sample mean of X. Also, we can calculate standard deviation of X. So sample mean is 4.64. And standard deviation of this is 0.6148. And now that we can see how reliable that this mean is. This standard deviation is standard deviation of observations. So if we take one more observation, then the deviation of that observation from mean is typically around 0.6. So that is the meaning of this standard deviation. And next, we want to check how reliable this mean is. Mean is already the mean of 5 observations. So that is more stable than just the one new observation. So mean of 5 observations. So we want to see how reliable that this observation is. And that is, we can quantify that reliability by the standard deviation of mean of X, or X bar. And the theory is here. So suppose that we have the n observations, and then standard error of X bar, or we can say standard deviation of X bar, is equal to standard deviation of one observation divided by square root of n. So in our case, 5 observations. So if standard deviation of X is 0.6, then standard deviation of mean of 5 observations is 0.6 over 5. That is around 0.12. Okay. So one observation, standard deviation is 0.6, but the average of 5 new observations, that should be more stable. So that has standard deviation of just 0.12. So that is the theory. So in this case, it's very simple situation. We are thinking about a very simple situation. We have just, independent and random variables from the same distribution. So in this case, we can calculate standard error of X bar as this quantity. So the standard error is calculated by 0.6148 divided by 5, square root of 5. Sorry, this is not 0.12, square root of 5, so 0.275. So 0.275. Yeah. So n gets larger, then standard error becomes arbitrarily small. So very large number of observations makes very reliable estimate for population mean. Okay, any questions so far? Okay, but this needs theory, right? So that we need the property of variance, or maybe some people may use central limit theorem to justify this. And this justification is sometimes very complicated. So here we have very simple assumption that these observations come from the same distribution. But what if these distributions are different? Then situation is more difficult to deal with. So another good way is just to simulate the standard error of X bar. And here is the answer. So we can calculate mean and the standard deviation by this way. And theoretically, we can calculate the standard error of X bar by standard deviation of X divided by square root of 5. But another way is to simulate this standard error of X bar. So here is the way to go. And this is actually resampling. Okay, so at first we prepare vector M, that is a vector of 100 zeros. Then we fill out this vector by this simulation. For I is equal to 1 to 100, that we take the sample mean of 5 observations with replacement. So X has 5 observations. So sample of X with replacement T. That is the 5 observations from original, these 5 observations, but with replacement. So that may be 3.9, 5.3, 3.9, 5.1, 4.1 or something. So we have allowed replacement. So some of the observations can be repeated twice or more, and some of the observations may not appear. But anyway, so we take 5 observations from this with replacement. So that is a kind of simulating new observations, right? We have these 5 observations. So that means in the population, we can guess that about 20% of the observations are around 5.1, another 20% is 4.8. So that is a natural assumption if we only have this data, right? So we just simulate the new observations based on existing observations. So that is what this code does. Then we take the mean, then we record it. Then we can simulate the sample mean 100 times. So that means we have X bar, 100 X bars, X bar 1 and X bar 2 and X bar 3 and so on up to X bar 100. So we have 100 X bars. So if we take standard deviation of those X bars, we can get estimated standard deviation of the sample mean. So that is 0.254. This is slightly smaller than this one, but still it's a reasonable estimate for this one. And if you don't have any statistical knowledge, mathematical knowledge, the method is easier than this method. Second method, you have to study variance or property of variance or something like that. But this one, just you can simulate it. So it's much easier. So that's the point. And yeah, so this is a way to estimate this. And of course, this number depends on your simulation. If you copy and paste this, you may get 2.69 or 0.269 or 0.281 or something like that. But you will get similar number to this one. We have some slight bias here because we have very small sample, only 5 observations. So assuming 20% of observations is exactly equal to 5.1 isn't probably correct assumption. So we have some bias for this one, but still, usually it's very good estimate. Any questions or comments? So this is doing slightly complicated thing.
Professor?
Hi.
Can you hear me?
Yes, yeah.
One question I have is that so you're saying that each simulation that we do, like it would be different each time we run this
yes.
Okay.
Yeah, so basically, yes, maybe I should try it. So we have X, right? So then mean of X is mean of X, but basically we sample from X replacement true. So replace. I think actually this should be replaced. Yeah. So we have 5 observations like this. Actually, this one just by chance 5 observations, but here we have 2 3.9s and the no 4.1. So we do this many times, and every time we have different. Maybe this one we have 3 times 3.9, or maybe this one we have 2 5.3s. So every time you get different number, and you can take mean of this. So every time you get different mean, then we can take standard deviation of these observations. So standard deviation of this 4.22 and 4.36 and 4.54 and 4.94. Then we get somewhat similar to 0.2. The true answer is 0.274. So 0.312 is not too far away from that. Yeah, so this is what we did, but for 100 simulations, not 4 simulations. Yeah. Yep. Any questions? This is similar to the situation for example, that you roll a die the 6 times and you get the maybe just 1, 3, 6, the 2, 4, 5, and just fortunately that you got the each number once each time. Then you assume that this number happens with probability 1/6. This number happens with probability 1/6, and so on. Then this simulating the 6 observations from this is a very natural way to simulate the 6 observations out of this experiment. Of course, sometimes your 6 observations are maybe the 1, 3, 1, the 2, 5, 4, or something like that. So if the original observations are a little, they are biased, then even if we sample from this, maybe always the mean of observations is maybe smaller than the expected value of 3.5. But yeah, this is a kind of reasonable way to simulate it. And this is called the so-called the bootstrapping. But the bootstrapping is these specific methods for resampling. Yeah. So this method is called bootstrapping, and the estimate is a good estimate for the theoretical standard deviation. Yeah, and bias becomes negligible when the sample size increases. In our case, we have only 5 observations. But if this is such as maybe just 20 or something, then this is very reliable estimate. We can get a very reliable estimate based on simulation. Exercise 1, we will try it later, to calculate the expected value for standard deviation of M in the previous slide. So in the previous slide, we simulate resampling 100 times, but it's also possible that we can consider all possible randomizations. We have 5 observations. So we have to choose x1, x2, x3, x4, x5. Each of x sub I have 5 possible ways. So that means in total, we have 5 to the 5th power permutations. So that is the 3,125, right? So 5 squared is 25, 5 cubed is 125. So 5 to the 5th power is 3,125. So if you try everything, then actually we can get the expected value for this simulation. And actually this is slightly biased from here, but it's pretty close to 0.2575. We can use for loop 5 times maybe to get this. Any questions? Have you ever studied bootstrapping or resampling methods? No. Yeah, maybe computer science majors they may have already learned, but this is pretty, the good breakthrough, right? So that if we have 5 observations, we cannot really observe the reliability of 5 observations because already 5 observations exist, but still we can check the reliability of those observations based on resampling methods. Okay, so next one, we start the random variables. And we have some basics. So first, mathematically speaking, a random variable is a map from a probability space to a set of numbers. Here, okay, so the map is a generalized version of function. So function, the maps the number to number, but the generally map maybe the start set or end set may not be a set of numbers. So maybe object to object. So the generalized version of function. And this map is from so-called probability space to a set of numbers. So actually the value is numbers, but the values are numbers, but the the initial set, the start set is the probability space, not a set of numbers. And the example here, suppose that we flip a coin twice, then the probability space is head head or head tail or tail head or tail tail. So first one represents the first outcome and second one represents the second outcome. So in total, we have 4 combinations. So this is not really a number. Right? So this is a so-called single event. So HH or HT or TH or TT. We have 4 cases. We distinguish the first and the second flips. And then suppose the X is the total number of heads when we do this trial. Then if the outcome is HH, then the number of heads is 2. So we can consider a map from these single events to numbers. HH to 2 and HT, that should go to 1, and TH goes to 1, and TT goes to 0. So this rule, X, is a map, and this is a random variable. So basically, the probability space is all possible outcomes of some probabilistic experiments. And the X, basically, is a rule that to correspond each single outcome to some number. So this X is one of the simplest example of random variables. Okay. And yeah, so sometimes this range is discrete, and sometimes this range is any number.
This is my probability class.
Hi, yeah.
I said I did this in my probability class.
You didn't take probability class?
No, I said I did this in my probability class.
Oh yeah, sure.
I did this in probability, the level 5 level course.
Yeah, it's just I want to make sure that everyone is on the same page. So some people take more applied statistics course before this. So yeah.
Yeah, I'm just saying that I took probability course already.
Yeah, I understand, and I think that many of you have taken, but just I want to make sure that everyone is on the same page. Okay, and if the values are discrete, we say this is a discrete random variables. If the value is any number, that we say this as a continuous random variable. So in this case, the possible values are just 0 and 1 and 2. So we say this as a discrete random variable. So discrete random variable is easier to describe because we only have finite cases. We only have countably many cases, typically finitely many cases. So for discrete random variables, we can just make a table of probabilities. So that is called probability mass function. So probability of X is equal to K is denoted as P of K, sometimes F of K, and this is called probability mass function. So our example is here. The possible values are just 0 and 1 and 2 in a flipping coin twice example. And if original event is TT, then number of heads is 0. That happens with probability, the 0.25, because if the result is head or tail with 50% probability, basically all 4 single events have probability of 1/4 each, 1/4 each. So that probability is 0.25 because we only have the single event TT, which results in the K is equal to 0. And K is equal to 1 with probability 0.5 because TH and HT becomes this event. And 2, only the HH becomes this event. So the probabilities are these. So just the point is that not all K's have the same probability. So we need this kind of table to describe probability distribution. And continuous case, this is a little bit more complicated, but basically we have corresponding function to P of X that is called the density function. So density function has this property. So basically, for continuous variables, it does not make much sense to think about probability of X is equal to A. For example, suppose the X is the temperature of some specific location at a random time, then X maybe the 20.5 degree or 70.6 degree or something, but the probability that X is exactly equal to 50 degree, that is 0. Right? So it makes sense to think about the probability of X is between 50 and 51. That's fine, but since the result may be any number, so we have to always specify range to consider probability. So probability of X is between A and B. So that corresponds to the area under the curve y is equal to f of x between x is equal to a to x is equal to b. So that is the way to define probability for continuous random variables. So f of x is a kind of continuous version of a histogram. Then we think about the area of the histogram to calculate the probability. That is the idea. So total probability is 1. So the probability of x is between negative infinity to positive infinity should be 1. And probability is non-negative. So this a kind of histogram, continuous version of a histogram, the value should be always non-negative. And the cumulative distribution function. Okay, so we have the probability density function, the PDF f of x, but we can also consider probability of x is less than some value. Maybe you can say probability of x is less than a, but here we replace a by lowercase x. And this is called the cumulative distribution function. So this is probably conceptually easier because always this probability is, this number exists. Regardless of type of x. X is discrete, this function is fine. Then continuous, also this function is fine. And naturally, this is the antiderivative of lowercase f of x because so this is the area of the area under the lowercase of f of x. So so the capital F prime of x is lowercase f of x. Any questions so far? I think you can refer the statistics or probability textbooks to find this. And our functions, we have 4 different functions. So D plus name, for example, D plus norm, NORM for the is a density function for normal distribution. And also P plus name, that is the cumulative distribution function, capital F. And the Q plus name that represents quantile function, that is the inverse of CDF. So that means that we calculate from probability to the threshold. And R plus norm, that this generates random number based on this distribution. So here is the graph, the diagram to explain that, the figure to explain that. So this is normal distribution. So this is bell-shaped curve, well-known bell-shaped curve. So this is a kind of continuous version of the histogram. So you can see this, the shadowed area. So this is the probability that x is less than this value, maybe 1.2. And this can be obtained by the p-norm function. So if you type p-norm of 1.2, then you get this area. So total area under the curve is 1. So probably this area is about maybe 0.8. And you can get this by the p norm of 1.2. And this is one function. And the q norm is the other way around. If you give 0.8, then you get this threshold value 1.2. So q norm of 0.8 becomes 1.2. Just approximate. Maybe you can do this. And a p norm of 1.2. Actually, this is 0.884. So maybe 1.1 or something. 1.0 maybe. Or even, sorry, maybe 0.8 or something. 0.9 maybe. P norm 0.9 is about 0.181. And the Q norm of 0.815, maybe 816, this becomes about 0.9. So Q norm is inverse. If you give area, then you can get threshold. And the D norm is the height of this function. So for example, if you plug in 0, D norm of 0 is the height of this, the highest point. You can type D norm of 0. That is 0.399 approximately. And actually that is about 0.399, you can see. If you input larger value, D norm of maybe 2, that is 0.05. D norm of 2 is this height, so it's very low, so 0.05, and so on. Then R norm. R norm is the function to generate random numbers. If we type R norm 3, it generates 3 random numbers based on this distribution. You can see that from this distribution, most observations are between -1 and +1. And actually, if you generate 3 random numbers, that is -0.61, 0.13, and -0.22. Maybe once again, then you get the -0.08, 0.6, -0.84. Maybe sometimes it exceeds 1. It does not exceed 1, but yeah, sometimes large numbers such as 2.45 or -2.33. Yeah. So these are the example of how these functions work in R. Any questions? Yeah, actually, so these are letters to explain the function. So P stands for probability, Q quantile, D density, and R random. And I think we don't use this many times, but this is the exact definition of normal density function. So that is 1 over sigma times square root of 2 pi times exponential of -x minus mu square over 2 sigma square. And the previous page that we just see the normal random variable. So that is this function with mu is 0 and sigma is 1. So population mean is 0 and population standard deviation is 1. But in general, we can define this random variable with positive sigma. Then we can use this function as we can use this function for our language, and that format is yeah. Actually, we can specify the population mean and the population standard deviation within the function, the P norm, Q norm, D norm, and R norm. Okay, so still, this is what I did the last time. D norm of 0 was 0.399, but also you can input multiple values in these functions. So D norm of -2 to 2, then we can calculate these 5 values at once. So like this. And if we want to make our line graph of this density function, then you can put like this. So this is a sequence from -4.00 to +4.00. So we can put in plot function, and x coordinate is these numbers, and y coordinate is the D norm of these numbers. then you can make a line graph of this. Then you can make this. So it almost looks like a smooth curve, but I connected the basically 801 points from -4, -3.99 up to 4.00. So here is I, and this is the d norm of I. So this is density function. And yeah, these are some examples. The p norm of 0 is the probability of x is less than 0. And the normal distribution is symmetric around x is equal to 0. So the left-hand side, the area is just half of the entire area, so 0.5. P norm of 1.96, that this is about 97.5%, 0.975. You can see left of x is equal to 1.96. You can see the almost entire area under the curve. So it is almost equal to 1, just slightly smaller than 1. Q norm of 0, if probability is 0, the threshold is -infinity. So probability of x is probability that x is sorry, maybe we go back Q norm. So the area is 0. That means the threshold is infinitely, negative. If we have some finite value, still area is some positive value. So Q norm of 0 is always -infinity. Capital F of x is approaching to 0 if x goes to -infinity. Q norm of 0, 0.5, this is the inverse function of P norm. So we get the 0.00, right? If the area is half, okay, so we have the area of 0.5, then threshold is 0. And Q norm 0.795, then we get the 1.96. This is opposite of this. And R norm here, we have already done that. And the D norm, P norm, Q norm function, also R norm function, we can specify mean and standard deviation. Yeah, so P norm of actually the 3.92. 3.92 is equal to 97%, because if we set standard deviation twice as large, basically the threshold, the threshold value also becomes twice as large for compared to the standard normal distribution. So P norm of 1.96, standard normal, mean 0, standard deviation 1 is 0.975. But if standard deviation is 2, if you multiply this number, then we get the same number. And Q norm, yeah, so this is just opposite of this. So we can specify mean and the standard deviation here. Any questions? Maybe we can do some exercises, and we will do exercise 4. You can see the website, and you can find the exercise 4 and also data for that. And maybe we focus on the first question, because second question and third question, we haven't done that yet. Maybe third one we have done that, but the first question. Okay, so we are analyzing the vector x. This is the we are investigating the risk to invest in stock X, and we have a data of 50 daily returns in percentage available in Canvas. This is return.csv file, and its sample standard deviation is 1.5598. Typically, this stock has standard deviation of 1.55. So maybe sometimes positive 1.55, actually the percent as daily return, sometimes negative 1.2. Then we want to see how reliable this standard deviation is. So just calculate based on bootstrap method to estimate standard deviation of sigma hat. So how reliable this standard deviation is. So you have to sample 50 observations from original 50 observations with replacement. Then you simulate this sigma hat. You repeat that hundreds of times. Then you take standard deviation of those estimated standard deviations. So that is what we should do. Okay, we set up the breakout room and to discuss this. How many students? We have, I don't know, 20, almost all students. So maybe we set up maybe 6 rooms. Assign automatically. So just I recommend one student share the screen. Okay, so enjoy your conversation for maybe 12 minutes, 10 to 12 minutes. Hi, Brianna. You should join the discussion. Yep.
Professor, you might be muted.
Sorry, thank you. Always, yeah. Okay, so we do the exercise, and sorry for the confusion, but the data set we should use is return.csv file. So I set the working directly, so we have to read the table and the return.csv. Return.csv, and we have, I think, the header here. So header is equal to true. Separation symbol is usually this for return.csv. Oh yeah, sorry. This is my directly is exercise 4. So then this. Okay, so we read this file. So this is the vector of 50 observations. And actually the X is within this data frame. So the $X is a vector. Okay, so we want to bootstrap this. So basically we want to sample this $X with replacement. So replacement is equal to true. So like this. Then we take standard.
You're sharing your screen.
Oh, sorry. Okay, sorry. So we set working directly here, and we read table. So the data set is return.csv. And after read the table, this is actually a data frame. So we want to get the $X to get these values as a vector. So $X is a vector with these 50 observations. So we want to sample this, then take standard deviation. So this. So this is one simulated the standard deviation. Okay, and we do this many times. So for I is equal to 100 to 300. So typically we say maybe 300 times is sufficient to calculate the value. You can do more, like 1,000 times to get more accurate value. So so maybe we have to set the result vector numeric 3000 first. Then the for I is equal to 1000, the y ith element is equal to standard deviation of this simulated result. Then, sorry, yi is equal to this one. Yeah, so we get some trouble. I is equal to, yeah, I think we have to close parentheses once more. So this, then we get the y values, just I see the first 6 values. So this is typically like 1.55, or maybe sometimes it's much smaller. Maybe we get maybe 10 observations. Yeah, so it's around 1.0 to 1.8. And we want to see how reliable this standard deviation is. So we take the standard deviation of y. So my answer is 0.354. So if you repeat this, maybe you get a different answer, but this is what we want to see. Yeah. Sorry, I think that some rooms get to 0.22 or something. I don't know what's wrong with that. Maybe just by chance, or yeah, I don't know. But my answer is 0.354. Maybe you can try this once more. Sorry, this one. Then once again, standard deviation of y. So I think the answer should be somewhere between 0.35. Maybe once more. Yeah, about 0.35. That should be an answer. Okay, so that's it for today. And I checked the attendance, and I got the chat. Can anyone use the, oh yeah, sorry, yeah. And the value, yeah, my recommendation is maybe 300 to 1000 for this bootstrapping. Yeah, maybe more serious publications, maybe you can use 100,000 times, but maybe 300 to 1000 is appropriate. value. Okay, so that's it for today, and let's see you on Thursday.